Welcome to more enthalpy of reaction. You remember that fun problem just before this where they gave us the delta H for the reaction? No more Mr. Nice Guy, apparently. This one, we're going to need a delta H, and they have not given it to us, so this is going to get a little labor intensive. A 2.5 gram sample of sucrose is burned in a calorimeter, which contains 2.19 kilograms of water. Water increases. So there are two things going on here. We take some sugar and light it on fire. That releases some heat. Then that heat gets absorbed by a chunk of water, which warms up. And we're going to have to work both sides of that to solve this thing. Calculate the heat absorbed by the water. So at first, we're just going to focus on the water side and forget about the sugar. We'll get to that in a moment. We're just saying, magically, we had 2.19 kilograms of water. It heated up from 20.5 to 2501 degrees. How much heat would that have taken? And we have a formula for stuff heating up, which says energy equals mc delta T. The mass for this water is 2.19 kilograms. As soon as I write kilo here, I'm committed to working in kilo units. So when I write the specific heat for water, I'm going to say 4.19 kilojoules per kilogram degrees Celsius. You can work in joules per gram or kilojoules per kilogram, but you can't mix and match. So this whole problem, or this whole section at least, I'm going to be in kilo. And temperature change from 0.5 up to 2501 is 4.51 degrees. Celsius. And if we mash calculator keys, we get 2.19 times 4.19 times 4.51 is 41.384 kilograms canceled, degrees canceled, kilojoules. So the water must have absorbed 41.384 kilojoules to warm up the way it did. Now we can turn to the sugar and say, obviously you just released 41.384 kilojoules when you were burning. You're where this energy came from. So on the sugar side, we can say this happened during the chemical reaction. Total energy, 41.384 kilojoules. That's what came out of our sugar burn. Equals number of moles. We don't have it. Side calculation, we need to get the number of moles for sucrose, and this one is a little bit of a chore. Number of moles equals mass over molar mass. Mass is 2.5 grams. They told us that in the problem. That's the easy part. Molar mass of sucrose. If you don't know what sucrose is, you can look it up in the data book in the heats of formation table. It is C12H22O11. And because of all those numbers, it's got a honkin' molar mass. 12 carbons is 144.12. 22 hydrogens is 22.22. Hydrogen's easy. And 11 oxygens is 176.00. 4, 1 plus 2 is 3, 6 plus 6 is 12, 5, 7, 14, 342.34 is the molar mass for table sugar. 2.5 divided by 342.34 gives us 0.007303 moles. You remember in the previous example, I rounded a little too hard, and so my finished answer was off by 0.01, and that bugged me. So you may have noticed I'm carrying a weirdly high number of decimals here. We'll see if we can avoid that happening again. So total energy, there it is. Number of moles, there it is. Delta H, don't know, I want to find it. So that's our delta H that we're solving for. We solve this by dividing both sides by 0.007303, and that gives us 41.384. Delta H equals 5,666.9. You know what? On the calculator, I used the unrounded version of this, and that's going to give weird results. So let me run this one more time. 41.384 divided by 0.007303. Not all that different. I'm a bit paranoid, it seems. 5,666.7 kilojoules per mole of sucrose. And write a balanced thermochemical equation. The combustion of sucrose means sucrose reacts with oxygen, just like any other hydrocarbons. So we have C12H22O11. That's sugar. When stuff burns, or at least when hydrocarbons burn, they react with oxygen. And the main products are carbon dioxide and steam. They asked for balanced, unsurprisingly, so how do we balance this? 12 carbons means we need a 12 over here. 22 hydrogen means we need 11 over here. Now, oxygen. 12 times 2 is 24 oxygens. 11 more here gives us a total of 35 oxygens on the right-hand side. On the left side, we have 11 oxygens right here. 35 minus 11 is... Okay, so we need a total of 35 oxygens. 11 of them are already covered here, so we need 24 more. This needs to be 24 oxygens, and we can accomplish that by putting a 12 on it. Good? This is still not a thermochemical equation, but at least it's a balanced equation for the combustion of sucrose. And if we want to make it thermochemical, we have to put this delta H in it. And there are two ways you can do that. Way number one is you can write the heat in as if it were a chemical species and just say, this reaction will make, among other things, 5,666.7 kilojoules. Or, separate from the reaction, you can say delta H equals negative 5,666.7 kJ. Hang on a minute, Mr. Fay. How did you know this was exothermic? Where did that negative come from? How do we know this is exothermic? If you've ever lit sugar on fire, you know it's exothermic because you would have felt the heat and seen the scorch. But from this description, the key fact is this reaction happened near some water, and what happened to the water? Got hot. If your surroundings are heating up, that means you're throwing energy into them and your reaction must be exothermic. If this water were getting colder, that would mean your reaction is sucking energy out of the surroundings, and we'd call it endothermic. But the fact that the sugar reaction is giving us hot water means the reaction is exothermic and the energy is coming out. Now, for these answers, I gave 5 significant digits for the delta H. If we were being good about our sig digs here, 4 sig digs for our delta H. Our mass only had 3 sig digs. The specific heat for water, as far as I know, is 4.19, so if we're using the number out of my brain, that's only got 3 sig digs. And this mass is also 3, so that means this 5,666.7 is too much, and we should be rounding this to 5.67 times 10 to the 3 kilojoules. That's the best we can do using only 3 significant digits. A little bit more about that in case you're weirded out. You start with 5666.7. We want to take this down to 3 digits, but you can't write 5,666 using only 3 digits, so 2 steps. First, we change this to scientific notation. Move the decimal 3 steps over, and we get 5.6667, sorry, times 10 to the, this was 3 jumps, so 10 to the 3 kilojoules. This is scientific notation with 5 sig digs. Then we round it to 3 sig digs. We say we're keeping these 3 digits. Do I round up? Yeah, that's 5 or more, and that's how we land on 5.67. Maybe you knew that part already, but just in case, that's how we do the rounding. And if we were writing this as a delta H, it should technically also have the negative sign on it to remind us that the reaction's exothermic.